Welcome to another video. So in this video I am trying to solve another previous year KTU problem. This is from MoS S3 Civil. This is from the fourth module. Okay, this is a theory problem. So this problem I will solve in three parts. So this is the first part video. So 2017 December they asked derive the classic bending equation. Okay, so this we'll do in the next two videos. What is pure bending? Derive an expression for bending stress in beams stating the assumptions. So this is another part. One part of this we will solve in this video. This was in 2018 April for 15 marks. Then 2019 May it was asked what do you mean by pure bending? Sketch an example of beam subject to pure bending. Okay. So these three questions they are very related. It's a very important theory problem from KTU. You have to study this. Among this assumptions of bending. Okay, simple bending. What are the assumptions? This I have taken from R.K. Bensal. This direct snap from the R.K. Bensal book. There are 6 assumptions. I will just explain what are these assumptions. Okay, then we will see what is this is basically assumptions of pure bending. Okay, theory of bending. Before discussing the theory of simple bending, the important assumptions are the material of the beam is homogeneous and isotropic. Now, what do you mean by homogeneous? What do you mean by isotropic? Homogeneous means any part of the material you take, you get same properties. Okay, so if you have a beam, okay, so you take one small portion here and the small portion here. So these two portions will have same properties. That means the density of the portion will be same. Okay, porosity will be same. All those things will be same. Generally, steel is a material which we can assume to be homogeneous. Concrete is actually not homogeneous material, but for all practical purposes, we'll assume it to be homogeneous. Okay. Now, isotropic gives the idea that the property in the direction is same. So, for example, a material can have. So let's say if you apply some force in this direction, okay, it will elongate. The elongation is depending upon Young's modulus. Now, if you apply force in this direction, it will elongate in this direction. Okay, so confuse it. So it will change, elongate. This elongation depends upon Young's modulus. Now, if you apply the force in the other direction, it will elongate in this direction. Okay, so this also depends upon Young's modulus. Now, it is always possible that the Young's modulus of this and Young's modulus of this can be different. The both directions, the Young's modulus can be different. Okay. Now, for an isotropic material, what they are telling is the Young's modulus and all other properties of the material. So, for example, Poisson's ratio, modulus of rigidity, all those things doesn't depend upon the direction. All direction it will be same. Okay. So, whatever MoS, S3 MoS, what we are dealing with, all the materials that is isotropic. Okay. So, all assumptions give us isotropic. Now, the value of Young's modulus of velocity is the same in tension and compression. So, this is self-explanatory. A material which can be in compression or which can be in tension. Okay, both will have same Young's modulus. Young's modulus will be same. So, Young's modulus can be different in compression and tension. So, we can see that concrete is very weak in tension. Its Young's modulus in tension is different from that is a compression. But we will assume it to be same. For all practical purposes, with respect to bending moment, where bending stresses are coming, this is assumption. This is okay. The transverse sections, which is plane before bending, remain plane after bending. This is an important assumption. You have to write this assumption. This is very important assumptions. One of the I would say this is the most important assumption of the simple bending theory. Now, what happens? We know that when beam bends, there is a small, if the beam obeys Hooke's law, then there will be a line passing through the centroid of the beam. This centroid of the beam, this is also known as neutral axis. Okay. Now, if you take a section, any section, vertical section like this, okay, it's transverse sections. Transverse is basically perpendicular to longitudinal direction. So, any section you take, this beam after bending, so it will bend like this. The neutral axis also will be like this. So, okay. Now, this section initially it made an angle 90 degree with the neutral axis. So, after bending also this angle will remain 90 degree. So, take another section here. This is also 90 degree. It will become like this. degree. Okay, this is the meaning of this. What they're telling is this section will not be, become like this. It will not become like this. It will not become like this. Okay, so this, whatever which is plain, it will remain plain after bending also. That is the meaning of that. This is assumption. For small bending, this assumptions is very much valid. We can for small bendings which we are using for bending equation, this is very much bending. So basically the bending equation which we are using, it is for beams, concrete beams, steel beams. The bending is actually very small. For example, if you have a beam in the room which you're sitting, you look at the beam, that beam is actually in a bent shape, but it is so small that you will not recognize that. Okay, so we assume this theory for those kind of beams where the deflection or the bending is very small. Then the beam is initially straight and all longitudinal filaments bent into circular racks of common center of curvature. So what they're telling is, if you take a very small portion here, okay, so that portion will, after bend, it will become like this. Okay, and what they're telling is all these are part of a very small circle, or not very small circle. These are actually very small arcs of a circle. So that is another assumptions. So all this bend shape. So whatever bend shape is there, if you take a very small element, this is for very small element. Okay, then all these small strips, if you consider, those strips will bend, and that strips will form will be a part of an arc of a circle. So that is another assumption. Okay, the radius of the curvature is large compared to the dimension of the cross section. So the radius of curvature is basically, so I told you there is a circle. So this is a part of a circle. So if I complete the circle, the radius of that circle is what is known as radius of curvature. Now what they're telling is the radius of curvature is very large. Okay, so basically when the circle becomes very large, this curved line become almost a straight line. So that is what the assumption is. This assumption is okay. Then each layer of beam is free to expand and contract independent of the layer above or below it. Okay, so basically if you say this there is one layer here, there is another layer here, below this. This layer, the top layer, can reduce its length or increase its length without depending upon the layer in the below. So basically it is counterintuitive, because assume they are basically one and the same layer. They are they are stuck with each other, but what they're telling is they are free to move with each other. Okay, so that they're free to move. It's an assumption. Okay, so these are the important assumptions. Now make sure that you write this assumption. Third assumption is very important. Okay, all other assumptions are also important. Homogeneous is important. Young's modulus is important. So but these are the 6 assumptions that you should remember. Okay, so this is about assumptions of bending equation. Okay, so this is the assumptions of bending equation. Now what is pure bending? That is another thing that I have to deal with in this video. So pure bending is nothing but beam subjected to only bending moment and no shear force. So how can that happen? So that can happen in many ways. So let's say if you have a cantilever beam, and I apply a bending moment here. So if you see here, there will be a reaction moment here of the same magnitude, and all the section of the beam will be having the same bending moment. So the bending moment will be like this. Okay, this is bending moment diagram. Shear force diagram, there will be no shear force, because there will be no shear in this beam. So you can assume that, or you can see, assume that there is a shear force. Use vertical equilibrium. So vertical equilibrium will tell me that V equal to 0. Okay, there is no vertical force in the beam, so there is no vertical shear or reaction. So there is no shear force. Okay, so this is one way in which we can have bending, pure bending. So that means only bending moment is there. Another way is a very common method. So that is basically a 4-point loading method. This you will study in the higher semesters. It's an experiment for your higher semesters. So if you have a simple supported beam, okay, what you do, you put loads in two loads in the symmetrical way. So this is W, this is also W. Okay, and these distances are also same. A. Okay. Now, if you find the reactions, you'll find that reactions are same as W. These are the reaction. Okay. Now, if I draw the bending moment diagram for this, so this you can take up as an assignment or something. So bending moment diagram looks like this. Okay, and shear force diagram looks like this. Shear force diagram, this bending moment diagram. Okay, so this shear force value will be W. Bending moment value you can calculate, W into A will be the maximum value. So I hope you are able to calculate this. Otherwise, you can see the bending moment shear force videos. Okay. Now this beam also, if you observe this portion of the beam, okay, this portion of the beam there is only bending moment, no shear force. So this portion of the beam also is in pure bending. So this is a very important setup. So this is how you find the bending strength of a beam. If you have a wooden beam, you want to find at what moment it is going to break, which is also known as bending strength. What you do, you put loads like this. You increase the load same way. WW you keep on increasing. The load should be same. W. So actually in experiment when you are doing, how you will do this is it's pretty interesting. So I will just draw that also, so that you can have a feel of that. So what you will do, you get the beam. So let's say you are doing it on a wooden beam. So you put a wooden beam here. Then what you will have above the wooden beam, what you will keep? You will keep small 2 rollers, steel rollers at same distance. So same steel rollers is this is A, this is A, this is A. Okay. Then over the steel roller, what I will keep? I will keep a very strong steel beam. Very strong steel beam. So this beam is very rigid so that it will not bend. Okay, it is so rigid. Then what I will do? I will apply load in the center. Okay. Now what happened? This load will be distributed half to the board. So this there will be P by 2 here. There will be P by 2 here. So this will become this arrangement. Okay. This is one and the same. So this is how you actually load in the experiment. So there will be support here, some kind of support here. So this I think you will do in the 4th semester or something. Right, this is what is known as 4-point loading. 4-point loading because this is one reaction, this is another reaction. So on the beam there are 4 loads. There is this reaction, this load, and this load. That is why it is called 4-point loading. This is to find the strength of the beam. Now for this also, for basically what happens, this beam will crack here at some P. Okay, so using that you can find what is at what bending moment it has failed, and that is a bending strength of the beam. Okay, so this is basically pure bending. Now why is it always related to this? Why did I combine this? Because this assumptions or bending theory is actually derived for cases of pure bending. But in practical cases, you can also apply this theory on the beams where shear force also is present. Okay, but this is basically derived for pure bending case. So that is why this always comes along with this bending theory. So I hope this is clear. This is a part 1 of the video. The second part of the video, I'll start with derivation of bending equation. It's a very important derivation from your exam point of view. So please don't miss that out. We will see in the next part of this video. Thank you.